Hi students, this is Lakshmi Pallavi, Assistant Professor of PSH Mathematics, BV Raju Institute of Technology, Narsapur. I am going to teach course Linear Algebra and Calculus, and in that we will see Unit 1 Matrices. So, in the last class already I have told you what is, we have seen what is the definition of a matrix and what are the types of matrices and what are the uses of matrices and why actually are we using matrices. So, as a continuation of it, let us see today orthogonal matrix. Orthogonal matrix. So, when do we say a matrix is an orthogonal matrix? So, we say that a matrix is an orthogonal matrix if A into A transpose equal to I. If A into A transpose equal to I, then we call such a matrix to be an orthogonal matrix. And let us see one theorem. So, the theorem is every square matrix can be expressed as the sum of symmetric and skew symmetric matrix in a unique way. Yeah. What is the statement now? Every square matrix can be expressed as the sum of a symmetric and skew symmetric matrix in a unique way. Okay. So, from this, let A be a square matrix. Okay, let us assume that A is a square matrix. Now, this matrix A, I am writing it as half into A plus A transpose plus half into A minus A transpose. How are we writing this, ma? We are writing it as half into A plus A transpose plus half into A minus A transpose. So, this first one we will assume it as P and this second one we will assume it as Q. How are we assuming? Na? The first one we are assuming it as P and the second one we are assuming it as Q. So, when we add it up, when we add this P and Q together, you will get back the matrix A. Okay, when we add P and Q together, we will get back the matrix A. And here, as he said, every square matrix can be expressed as sum of symmetric and skew symmetric matrices. Now here what we have taken? We have taken two matrices P and Q. So now what we have to show? We have to show that P is a symmetric matrix and Q is a skew symmetric matrix. So that these two matrices are expressed as sum of a symmetric and a skew symmetric matrix. So now we have to show P is symmetric and Q is skew symmetric. What do you mean by a symmetric matrix? A symmetric matrix is a matrix in which P transpose equal to P. Suppose if P transpose equal to P, then we call such a matrix to be a symmetric matrix, and if P transpose equal to minus P, then we call such a matrix to be a skew symmetric matrix. Okay. Now, let us take the first one, that is P equal to 1 by 2 into A plus A transpose. Okay. Apply transpose on both sides. P transpose equal to 1 by 2 into A plus A transpose whole transpose. 1 by 2 into A plus A transpose whole transpose. Now what is this equal to? P transpose equal to 1 by 2 into A transpose plus A transpose whole transpose. Okay, that is nothing but 1 by 2 into A transpose plus A. Yeah, how we have written this much? Since we know P plus Q whole transpose equal to P transpose plus Q transpose. From there, A plus A transpose whole transpose can be written as A transpose plus A transpose whole transpose. And also we know A transpose whole transpose is A. So, what we got? 1 by 2 into A transpose plus A. That is nothing but equal to P. Therefore, P is symmetric. Therefore, what we can say? We can say P is a symmetric matrix. Now, let us take Q. What is Q? 1 by 2 into A minus A transpose. Okay. Now, apply transpose on both sides. Q transpose equal to 1 by 2 into A minus A transpose whole transpose. Okay. So, this is equal to 1 by 2 into A transpose minus A transpose whole transpose. This is again equal to 1 by 2 into A transpose minus A. 1 by 2 into A transpose minus A. If you take minus common, minus 1 by 2 into A minus A transpose, that is nothing but minus Q. Therefore, Q transpose is equal to minus Q. Therefore, Q is skew symmetric. Q is skew symmetric. Okay. So, the first part of the theorem we have proved. What is the first part of the theorem? Every square matrix is expressed as the sum of a symmetric and a skew symmetric matrix. Now, the second part of the theorem. What is the second part of the theorem? That this matrices is expressed in a unique way. So, now, finding the uniqueness. Let us see the uniqueness. So, in order to prove the uniqueness, what we will assume is, we will assume that there is some other matrix which is of this kind, and then we will show that some other matrix is nothing but our R and S. Okay. So, coming to the uniqueness, if possible, okay, if possible, assume that if possible, assume that A equal to, before we've taken P and Q, no? So we will take R and S. If possible, assume that R plus S be another such representation. If possible, assume that let A equal to R plus S be another such representation. Okay. So, when A equal to R plus S, we know R is symmetric and S is skew symmetric. Because it is same kind of representation again. So, R is symmetric and S is skew symmetric. That means R transpose equal to R and S transpose equal to minus S. R transpose equal to R and S transpose equal to minus S. Therefore, A equal to R plus S, then A transpose will be equal to R plus S whole transpose, that is R transpose plus S transpose. But since R transpose equal to R, you can write R and S transpose equal to minus S. So, A transpose will be equal to R minus S. A transpose will be equal to R minus S. Now, 1 by 2 into A plus A transpose. Let us consider 1 by 2 into A plus A transpose. That is equal to 1 by 2 into R plus S plus R minus S. And 1 by 2 into A minus A transpose will be equal to 1 by 2 into R plus S minus R plus S. Minus R plus S. So, here it is R and here it is S. So, 1 by 2 into A plus A transpose is R. 1 by 2 into A minus A transpose is S. But actually what is 1 by 2 into A plus A transpose according to the theorem which we have proved just now? That is nothing but equal to P. And 1 by 2 into A minus A transpose, just now we have seen, it is nothing but Q. So, whatever we have assumed, we thought that there is some other R and S, but that some other R and S is nothing but our P and Q only. Therefore, we can say the representation is unique. The representation is unique. Hence proved. Hence proved. Okay. Now, let us see what do you mean by. Till now, we have seen matrices in which we were entering the elements, or there were few elements in the matrices, right? So, if the elements in the matrices are real numbers, then we call such a matrix to be a real matrix. A real matrix is a matrix in which the elements in the matrix are real numbers. And then we have complex matrix. Complex matrix is a matrix in which the elements are complex numbers. Yeah. Like suppose this is a matrix A and we know what is a complex number, right? It is A plus IB where I square equal to minus 1. Where I square equal to minus 1 where I is the complex number. So, a complex matrix can be like this 2 plus 3i, 2 minus 3i, 5i, 8 plus 7i, something like this. This is a complex matrix in which the elements in this matrix are complex numbers. Yeah. So, such a matrix is called as a complex matrix. Now, 2 plus 3i is a complex number. Suppose you say this is small a. Okay. Then, conjugate of this complex number. Conjugate of this complex number, that is A bar equal to 2 minus 3i. Conjugate of this A is A bar, that is 2 minus 3i. Suppose you have minus here, then in the conjugate you will have plus. Okay, so this is called conjugate of a complex number. Then suppose this is the matrix A, then conjugate of A. Conjugate of A is A bar. Conjugate of A is A bar, and in this A bar you will get all the whatever numbers are there, complex numbers are there in A. If we write the conjugate of those complex numbers, then it is called as conjugate of A bar. That means here you have A, this no. So conjugate of A is A bar, that is 2 minus 3i, 2 plus 3i, minus 5i, 8 minus 7i. This is called as conjugate of the complex number A. Sorry, conjugate of the matrix A. And conjugate of the matrix, whenever you have this, we have few properties. A bar whole bar equal to A. This is the first property. A bar whole bar equal to A. And the second property is A into B whole bar equal to A bar dot B bar. A into B whole bar equal to A bar dot B bar. And the third property is A plus B whole bar equal to A bar plus B bar. A plus B whole bar equal to A bar plus B bar. So, this is a complex matrix and the conjugate of a complex matrix. Then we have transposed transposed conjugate of a matrix. Transposed conjugate of a matrix. Transposed conjugate of a matrix. Suppose A is a matrix and its conjugate is A bar and conjugate is A bar. And for this A bar, if you find a transpose, it is called as transposed conjugate of a matrix. That is A bar whole transpose. Yeah, A is a complex matrix and conjugate of A is A bar. A is a complex matrix and conjugate of A is A bar. Then transpose of the conjugate is A bar whole transpose. Okay. This can be written in two ways, ma. You can also write A transpose whole bar. Anything will give you the same answer. Okay. We can write A bar whole transpose or A transpose whole bar. Both of them will give us the same answer. And this is represented as A power theta. It is taken as A power theta. So, what is A power theta, ma? A bar whole transpose. Suppose this is, you have a matrix A, 5 plus 7i, 2 minus 3i, 8i, 4 minus 15i, suppose. 4 minus 15i. Suppose this is a matrix, then A power theta will be A bar whole transpose. So, first find A bar, that is 5 minus 7i, 2 plus 3i, minus 8i, 4 plus 15i. And find the transpose of this. So, that will be 5 minus 7i, 2 plus 3i, minus 8i, 4 plus 15i. So, this is called as A power theta or transposed conjugate of a matrix. Okay. And unitary matrix. Unitary matrix. If A into A power theta equal to I, then we call the matrix A to be a unitary matrix. Okay, we call the matrix A to be a unitary matrix if A into A power theta equal to I. And if A is unitary, then A transpose and A power theta are also unitary. A transpose and A power theta are also unitary. And A comma B are unitary. A comma B are unitary. Then AB is also unitary. Then A into B is also a unitary matrix. Okay. This is about unitary matrix. Then let us see few problems on this and then we will move on to our next topic, that is rank of a matrix. So before moving to the rank of a matrix, let us see few problems. Let us see first problem. Find A comma B comma C when we are given a matrix 0, 2b, C, A, B minus C, A minus B, C. 0, 2b, C, A, B minus C and A minus B, C it is an orthogonal matrix. If it is an orthogonal matrix. So, already we have seen today what is an orthogonal matrix, ma'am? Yeah? We have seen today. See, if A into A transpose equal to I, then we call such a matrix to be a orthogonal matrix. So, here what we can say, A into A transpose equal to I, because he said that this matrix is an orthogonal matrix. Now let us find out A transpose. what will be A transpose? 0, 2B, C, A, B minus C, A minus B, C. Okay. Now, A into A transpose equal to I. So, multiply A into A transpose. That is 0, 2B, C, A, B minus C, A minus B, C into A transpose is 0, A, 2B, B minus B, C minus C, C. Okay. Now multiply A into A transpose. When you multiply A into A transpose, what are we getting is 4B square plus C square. Yeah. 4B square plus C square. 2B square minus C square minus 2B square plus C square. And 2B square minus C square, A square plus B square plus C square. And then if you multiply A square minus B square minus C square, then here A minus 2B square plus C square, then A square minus B square minus C square, then A square plus B square plus C square. A square plus B square plus C square. Now this is equal to the identity matrix, that is 1 0 0 0 1 0 0 0 1. This is equal to the identity matrix 1 0 0 0 1 0 0 0 1. Now let us equate the corresponding elements and find out A comma B comma C. Okay. So when we equate the corresponding elements, what we are getting? 2B square minus C square equal to 0 and A square minus B square minus C square equal to 0. So 2B square minus C square equal to 0. That means C square equal to 2B square or C equal to plus or minus root 2B. C equal to plus or minus root 2b. Now if you put it here, what we can get? A square minus B square plus 2B square, minus 2B square equal to 0. So A square equal to 3B square or A equal to plus or minus root 3b or A equal to plus or minus root 3b. Now we have 4B square plus C square equal to 1. So 4B square plus 2B square equal to 1. 6B square equal to 1. That means B equal to plus or minus 1 by root 6. Plus or minus 1 by root 6. This value of B, if you put in C and A, then we will get C equal to plus or minus root 2 into 1 by root 6 or C equal to plus or minus 1 by root 3 and A will be plus or minus 1 by root 2. 1 by root 2. So we got what are the values of A plus or minus 1 by root 2, B equal to plus or minus 1 by root 6 and C equal to plus or minus 1 by root 3. Okay, got it everyone? Yeah, we have taken the matrix A and then he said since A is an orthogonal matrix, he has asked us to find out the values of A, B and C. So we have multiplied, as it is an orthogonal matrix, we have taken A into A transpose equal to I and from there we have multiplied A and A transpose and we have equated it to I and then we have got the values of A, B and C. Okay, let us do one more problem. Is the matrix A equal to 1 by 2 into minus 1, 1, 1, 1. 1 minus 1, 1, 1, 1, 1 minus 1, 1 and 1, 1, 1 minus 1. This is a 4 by 4 matrix. Is this matrix orthogonal? Yeah, he is asking us whether this matrix, the given matrix A, is orthogonal or not. So we know for a matrix to be orthogonal, what it should satisfy, ma? A into A transpose should be equal to I. Then only we can say that the matrix is an orthogonal matrix. So we are given the matrix A. Find out A transpose. A transpose will be 1 by 2 into minus 1, 1, 1, 1. Then 1 minus 1, 1, 1. 1, 1 minus 1, 1. 1, 1, 1 minus 1. So we can observe that A and A transpose are both one and the same. Now let us multiply A into A transpose. Let us multiply A into A transpose. 1 by 4 into, yeah, this is 1 by 2 and we have one more 1 by 2. So it is 1 by 4 into minus 1, 1, 1, 1. 1 minus 1, 1, 1, 1, 1 minus 1, 1, 1, 1, 1 minus 1. Yeah, just multiply both of them. It is simply like a square, right? So, 4 by 4 matrix multiplication is very similar to 3 by 3 matrix multiplication. So, simply multiply both of them. So, you will get 1 plus 1 plus 1 plus 1 plus 1, that is 4. And here if you see minus 1 minus 1 plus 1 plus 1, 0. And here also it will become 0, 0. Then this will be 0, 4, 0, 0, 0, 0, 4, 0, 0, 0, 0, 4. Here you can check it by yourself by simply multiplying each and every column with the each and every row with the corresponding column. Okay. So this is equal to 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1. So this is nothing but the identity matrix. This is nothing but identity matrix. Therefore, we have started with A into A transpose and we've got A into A transpose equal to I. Therefore, we can say that A is an orthogonal matrix. A is an orthogonal matrix. Okay, ma? Let us see one more problem. Prove that the matrix A is unitary. Matrix A is unitary and hence find A inverse if A equal to 1 by 2 into root 2 minus I root 2 0, I root 2 minus root 2 0, 0, 0, 2. Okay, suppose this is the given matrix A. Okay, first what we have to show, we have to show that the matrix A is a unitary matrix and hence we have to find A inverse. So, we know a matrix is unitary. When do we say that a matrix is unitary? If A into A power theta equal to I, then it is unitary. We say that a matrix is unitary if A into A power theta equal to I. So, for this first what we have to do? We have to find A power theta. So, what is A power theta, ma? A bar whole transpose. What is A power theta? A bar whole transpose. You can do it in the other way also. A transpose whole bar or A bar whole transpose. Anything will give you the same answer. So, this is the matrix A. First find out A bar. A bar will be 1 by 2 into here root 2 I root 2 0 minus I root 2 minus root 2 0 0 0 2. Yeah, we change the sign only for the complex numbers. Other numbers we write as it is. So, now you calculate A bar whole transpose. That is equal to 1 by 2 into root 2 I root 2 0 minus I root 2 minus root 2 0, 0 0 2. This is A bar whole transpose, or this is nothing but A power theta. Now let us multiply A into A power theta. So 1 by 2 into root 2 minus I root 2 0, I root 2 minus root 2 0, 0 0 2. Yeah, here we have 1 by 2 and 1 by 2. No? So let us write 1 by 4. And here it will be root 2 minus I root 2 0, I root 2 minus root 2 0, 0 0 2. Yeah, multiply both of them. So 1 by 4 into, yeah, root 2 into root 2 is 2 plus 2, 4. Then here it will be 0. And here it will be 0 0 0 0. So this will be I root 2 into root 2 is plus I root 2 minus I root 2 0. Then this will be 2 plus 2 4. And this will be 0. And 0 0 2 to the 4. Okay. So what we are getting? 1 0 0 0 1 0 0 0 1. So A into A power theta equal to I. Therefore, A is a unitary matrix. Therefore, A is unitary matrix. A into A power theta equal to I. Therefore, A is unitary matrix. Then what he has asked us to calculate? We have to find A inverse. So, A into A power theta equal to I. Therefore, what we can say? A power theta equal to A inverse. If you send this A to the other side, A power theta equal to A inverse. Therefore, we want A inverse. Therefore, A inverse equal to A power theta. And what is that equal to? We have written it here. A power theta, that is 1 by 2 into root 2 minus I root 2 0. I root 2 minus root 2 0 and 0 0 2. Yeah. Understood, ma? Clear, everybody? Yeah, we have first shown that the given matrix is a unitary matrix, and also what we have done, we have calculated A inverse. Okay. Now, let us move on to the next topic. That is, before going to the rank of a matrix, we need to know few things. What are the elementary row operations? Okay. Elementary row operations. What are the operations which we are carrying out on rows? Okay. Suppose you have two rows. Every row is represented like this, Ri, Rj. Okay. Then the first operation which we carry out is interchange of rows. Interchange of rows. That is Ri by implication Rj. We interchange ith row with jth row. Ri by implication Rj. Then we can multiply any row with a non-zero scalar. Multiplying a row with a non-zero scalar. We can multiply a row with a non-zero scalar. That is, Ri implies k times of Ri, or Ri implies 1 by k times of Ri. Ri implies k times of Ri, or Ri implies 1 by k times of Ri. You can multiply a row with a non-zero scalar. Then the third operation, you can have multiplying a row with a scalar, multiply a row with a scalar, and add or subtract it, to another row, add or subtract it to another row. That means k1 times of Ri plus or minus, Ri implies K1 times of Ri plus or minus K2 times of Rj. Okay, so what we are doing, we are multiplying ith row with K1, jth row with K2, and you can add both of them or you can subtract both of them. And whenever we carry out this such kind of operations, always the row on the LHS is getting changed. That means in this case, Ri will get changed and Rj will remain as it is. Ri will get changed and Rj will remain as it is. Okay. These are the elementary row operations, and you cannot multiply two rows and you cannot divide two rows. Okay. And if the same operations are carried out on columns, if same operations are carried out on columns, then we call it elementary column operations. Then we call it elementary column operations. Okay, ma? If these operations are carried out on rows, then they are elementary row operations. If they are carried out on columns, then they are elementary column operations. Now, equivalence of two matrices. Equivalence of two matrices. You are given a matrix A. Okay. And on this matrix A, we are doing some elementary column operations or elementary row operations. What are we doing now? We are given a matrix A, and for that matrix A, we are doing some elementary row operations and some elementary column operations. Then, after doing those operations, we have got a new matrix, that is matrix B. What? We are taking a matrix A, we are performing some elementary row and column operations on the matrix A, and then after doing few operations, we got the resultant matrix as the matrix B. Then we say that A is equivalent to B. What do you call that? A is equivalent to B. It is not A equal to B. A is equivalent to B. Okay. And whenever A is equivalent to B, then whatever properties B is having, same properties A also will be having. So those properties are like determinant, rank, like this. There are few properties when two matrices are equivalent, then whatever properties the matrix B is having, same properties can be taken to the matrix A. Okay. Now, let us see the first thing, that is rank of a matrix. Rank of a matrix. Let us see the formal definition of rank of a matrix. If A is a non-zero matrix, if A is a non-zero matrix, then A is said to have rank R. A is said to have rank R if, number one, A has at least one non-zero minor, of order R. A has at least one non-zero minor of order R, and every R plus 1th order minor, of A is 0. Every r plus 1th order of A minor of A is 0. Then the rank of A, it is denoted by row of A, and that is equal to R. What is rank of a matrix, ma'am? If A is a non-zero matrix, then A is said to have rank R if A has at least one non-zero minor of order R. What is minor? Minor is the after deleting the row and column in which a particular element is present, whatever determinant we are getting, that is called as minor. So, A has at least one non-zero minor of order R, and every R plus 1th order minor, that means every minor which is greater than R is always 0. Then in such cases, we say rank of A is R. And A should be a non-zero matrix. And rank of a zero matrix is always 0. Rank of a zero matrix is always 0. If A is a non-zero matrix, then we can say A has at least one non-zero minor of order R, and every R plus 1th order minor of A is 0. Okay. Then we have few properties. The first property is when A equal to 0, that means a zero matrix, then rank of A is equal to 0. And the second property is rank of the identity matrix. Rank of the identity matrix is equal to n. That means whatever is the order of the identity matrix, that will become the rank of that particular identity matrix. Then number 3. If determinant of A is not equal to 0 and A is an n by n matrix, then rank of A is equal to n. Okay. If determinant of a matrix is not equal to 0 and that matrix is of order n by n, then rank of A will be equal to n. Then number 4. Rank of AB is always less than or equal to rank of A and rank of B. Rank of A is always less than or equal to rank of A and rank of B. Number 5. Rank of A plus B is always less than or equal to rank of A plus rank of B. Then number 6. Rank of A minus B is always greater than or equal to rank of A minus rank of B. Rank of A minus B is always greater than or equal to rank of A minus rank of B. Suppose A is a n by n matrix. A is a n by n matrix. Then rank of A will always be less than or equal to n. If A is a n by n matrix, then rank of A will always be less than or equal to the order of the matrix. Then the minimum value of the rank of a non-zero matrix, the minimum value of the rank of a non-zero matrix, the minimum value of the rank of a non-zero matrix is 1. Okay, if A is a non-zero matrix, then its minimum value of the rank will be 1. If it is a zero matrix, then only the rank will be equal to 0. And we have few methods to find the rank of a matrix. It can be calculated in two ways. That first one is echelon form. With the help of echelon form, we can calculate rank of a matrix, and also with the help of normal form, we can calculate rank of a matrix. There are two methods in which we can find the rank of a matrix. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.